Welcome to the next lecture of Electric Circuit Analysis 2. And in the last lecture, we have seen up to the superposition theorem. Now, today, we are going to start source transformation. As we have already mentioned for most of our previous discussion, that uh, these theorems and circuit analysis techniques, most of them are similar, except we are now doing operations with the complex numbers and phases. So the source transformation is also carrying the same principle and it has same type of formulation and transformation methods. For example, if we have some voltage source in series with some impedance as shown here, so it can be converted into a current source in parallel to the same size of impedance. The amount of current can be calculated using simple Ohm's law, that is Is would be equal to Vs divided by Zs. And we can also transform from current source connected in parallel to some impedance into a voltage source connected with series impedance like this one. Here Vs would be equal to Is times Zs. So we must keep in mind that this Z is impedance and it can be a complex number if we have inductive or capacitive uh, elements in the circuit. So in this way, using these two relationships, we can convert from voltage source connected in series with an impedance Zs to a current source Is connected in parallel with same impedance Zs and vice versa. So just an example in order to understand this whole principle. Sometimes we do need a source transformation in order to reach the final solution conveniently with respect to the other circuit analysis techniques. For example, in this example, we are asked to find the voltage drop across this 10 ohm resistor, and we are given with this 20 angle minus 90 voltage source in series with 5 ohm resistor, and rest of the circuit is as shown here. So, according to our basic definition, this part of the circuit will be repeated as it is here. We can see that nothing is changed in this part. It is same as before, only we have converted this voltage source in series with a resistor to a current source in parallel to the same amount of resistance 5 ohm. And how we do it? We do it like Is is equal to voltage source divided by its series connected resistance, and it is 4 angle minus 90 the response, and we can convert it like this one also from this minus 90 angle. And why we are doing this? We, in order to find the voltage across this 10 ohm resistor, what we are trying to do is we are now forming a parallel combination of these two elements here. Now this parallel combination would be found and then converted back to the voltage source like this one. So from in order to reach from here to here, what we did is we first found the parallel combination of these two, and then we have calculated the we have converted this current source to the voltage source by considering this voltage source in parallel to that one. So we have found the parallel combination of these two resistances like this one here, and then we have converted this current source connected in parallel to the impedance to a voltage source, and its magnitude is given here. So in the end, what we do is we apply simple voltage divider rule in order to find Vx, the voltage across 10 ohm resistor, as we have seen here. Thevenin and Norton equivalent circuits. These are also circuit simplification techniques in which we find the voltage drop across some given terminals and the impedance, collective impedance seen by the circuit at those two given terminals. In order to find the Thevenin equivalent, we find Thevenin equivalent voltage and Thevenin equivalent impedance across those 2 points, and for the Norton equivalent circuits we find the current flowing through a short circuited branch over there and the impedance across those two um, given terminals. So the working principle is similar as before. However, what is important is that we should take care about the complex numbers, and as we are mostly working with phasors. There's another important point to consider is that if there are the sources with different frequencies of operation, we must consider them separately instead of combining them to a single frequency or single circuit. So from Norton, in order to get the Norton equivalent, we can easily convert from the voltage, Thevenin equivalent voltage, and the series impedance, Thevenin equivalent impedance, to get the current, Norton equivalent current, and Thevenin equivalent impedance would be same. So just by using the basic principle of source transformation we have just seen in previous slides, we can convert the Thevenin equivalent circuit into a Norton equivalent circuit. So if the circuit has the sources operating at different frequencies, the Thevenin or Norton equivalent circuits must be determined at each frequency, and this will lead us to multiple circuits operating at different frequencies. We cannot get a single equivalent circuit. So just to look into further details of the Thevenin equivalent circuit, we just see this example. In this example, we are given these two A, B terminals. Across these two terminals, we need to find Thevenin equivalent voltage and Thevenin equivalent impedance. So first, in order to get the Thevenin equivalent impedance, what we do is we need to short circuit this terminal. This voltage source should be short circuited in order to get the Thevenin equivalent. So this circuit, this voltage would be removed. So resulting in we have now a short circuit between these two terminals, and the resulting circuit would be there's these two terminals, these two elements minus 6J and 8 ohm are in parallel because their first element, first terminal is short circuited here and another terminal is short circuited here. So this is what we can see from this simplified form of representation of this circuit. Similarly, the 4 ohm and J12 ohm are also in parallel, and this can be shown here across terminals AB. So now finding their parallel combination of each of them, the result would be the parallel combination of these two 8 ohm and J6 ohm, minus J6 ohm in fact, is in series with the parallel combination of 4 ohm and J4 ohm. We are going to find their parallel combinations here, and then the total Thevenin equivalent impedance would be a series combination of Z1 and Z2, and it's like this one. And in order to get the Thevenin equivalent voltage, we need to find the voltage drop across these two terminals. There can be multiple methods in order to get this voltage, what we do is we do find the current flowing through one of the branch and the another branch, and then uh, finding the voltage drop across a single element. For example, here what we do is the voltage drop across these two elements minus J6 and 8 ohm is 120 angle 75, and these two are in series connection, so total current flowing through them is given by this relationship. Similarly, this I2 current can be found by simply dividing this voltage by the total impedance. This is series impedance of these. So we now get the current I1 and I2. And in order to get the Thevenin equivalent voltage, we can apply KVL around loop B, C, D, E, A, and B. So this is B, C, D, E, A, and B. So by applying the simply KVL, we reach the final conclusion like this one. So this is our Thevenin equivalent voltage, and Thevenin equivalent impedance was found on previous slide. In this way, we conclude our calculation about this one. There's another form of circuits in which we do have this dependent source, not the independent current source or voltage source. So in this way, we do need to find or handle this circuit a bit differently, because dependent sources cannot be short circuited or open circuited like the dependent voltage sources, independent voltage sources, and independent current sources respectively. So what we do is we need to consider this current source all the time. So first we find the Thevenin equivalent voltage across terminals AB. So how we do it? We just get the currents at this node 1 so that we get this I0, and from this I0 we can calculate this current source as well. So firstly, at this node 15 ampere current is entering, whereas zero point 0.5 I0 current is leaving here and I0 current is going here. Why we are calling it 0.5 I0? We are calling it by I0 because this is the current flowing through this path, and the current flowing through this path is 0.5 I0. There is no current going there, so the current in flowing through this dependent current source is same as the current flowing through 4 ohm plus J 3 ohm. So that is why we have directly written 0.5 I naught here. So by solving this equation, we get I naught equal to 10 ampere. Then we apply KVL to the loop on the right hand side and get the VTH. On the right hand side, the voltage drop across this branch is same as the voltage drop across terminals AB, and which in turn is our Thevenin equivalent voltage. So what we do is we just apply our KVL and in this loop and get the voltage drop here. So how this works? It is simply I naught times 2 minus J4, and because this I naught is flowing downwards and we are taking upward direction, so that's why we are using minus sign here. Then the voltage drop across 4 plus J3 ohm is J plus 4 plus J3 ohm times 0.5 I naught, as we have already discussed, and plus the voltage drop here. This is Thevenin equivalent voltage. So in this way, by solving this equation, we find Thevenin equivalent voltage to be 55 angle minus 90. Now the point is to find the Thevenin equivalent impedance. For finding, in order to find the Thevenin equivalent impedance with the in the circuit with dependent current or voltage sources, what we do is we connect a current or voltage source at the terminals of consideration. That is the terminal across which we need to find Thevenin equivalent impedance and Thevenin equivalent voltage. and the value of this current or voltage source is not fixed. It is arbitrary. We can take any value of IS. For example, in this case, it's 3 ohm, 3 angle 0 ampere. We can take it like 100 angle 30 or 20 angle 90 or whatever. So it is not any uh, problem for if we take different values. And in shortly we will see that how this will not affect the result. So now for this case we have connected 3 angle 0 ampere source at the terminals where we need to find Thevenin equivalent impedance. Well, now what we do is we are now trying to get the Thevenin equivalent impedance, and the point and the style of getting this is that we find the current flowing into the circuit at this terminal and impedance seen at this and at these terminals, a voltage across these terminals, sorry. So after taking the ratio of voltage and current at these two terminals, we get to the final Thevenin equivalent impedance like this one. So how it works, we apply simply KCL. This 3 ampere is entering at this node, 0.5 I naught is leaving at this node, and I naught is flowing here because we are already given that I naught is flowing at this branch in our question. So that is why we can simply write the Kcl equation at this node. This is 3 is equal to I naught plus zero point 0.5 I naught, and from here we get I naught is equal to 2 ampere. So if I naught is 2 ampere, then applying KVL to the outer loop, this is outer loop, and we apply KVL, it will result into, we have this voltage Vs times this I naught times 4 minus J2 and 4 plus J3. This I naught current is flowing through both of these impedances. So the voltage drop across these two is I naught times their value. And in this way, we get this Vs very simply, like this. So now we have got this voltage drop across these two terminals, and the current flowing inward to the circuit is Is. So the resulting impedance would be Vs divided by Is. And from here we can see that if we have used this Is equal to, like for example, 6 angle 0, let us say we are using this current source instead of 3, then how will it affect? It will affect only like this value would be 6 instead of 3. Secondly, our voltage drop would differ slightly. In this way, the final result would remain the same. So finally, what we get is excuse me. Finally, what we get is that TH, and it will remain the same as in case of 3 ampere or 6 ampere. Moving on to the Norton equivalent circuit, as we have already mentioned, we can simplify this calculation by finding the Thevenin equivalent and then converting the same circuit by source transformation into Norton equivalent circuit. This is the easiest possible method to solve these type of circuits. So here what we do is that we need to find the current I naught. So these are the terminals at which we need to find Thevenin equivalent impedance and Thevenin equivalent voltage. And so one by one, by setting the sources equal to 0, we set this open circuit and we set this short circuit like here and here. The Thevenin equivalent impedance or Norton equivalent impedance can be found very easily. It would be the series combination. These all these impedances are short circuited by this branch, so this impedance would be 0 here, and only 5 ohm resistance will be equal to the Norton or Thevenin equivalent impedance in this case. In order to get the Norton current, what we do is we short circuit the AB terminals and apply the mesh analysis like this one and find the current flowing through this one. Alternatively, we could find the open circuit voltage across these two terminals by any means. So here, by short circuiting, there is a super mesh between mesh number 2 and 3 because there is a current source in between two non-reference meshes. So in this way, for mesh 1, the equation is like this one. We have J40 ohm voltage source. We have current I1 minus I2 flowing through 8 ohm and minus J2 ohm, and current I1 minus I3 flowing through 10 and J4 ohm impedances. So by writing the simply mesh equation, we can solve these. For the super mesh, the equation would be the current I2, I3 minus I2 would be 3 ampere, like this one. So by solving these equations, we can get the I naught and then alternatively the IN can be calculated. So this is our I naught value and IN value. So in this way, we could find the Norton equivalent and Thevenin equivalent. The students are encouraged to apply the technique of finding Norton equivalent circuit through the Thevenin equivalent method also, and they can see and confirm that both methods would result the same answer. With this, we end our today's lecture. Hopefully, we will meet in another lecture very soon. Thank you very much.